we have a channel section. Determine the moments of inertia for the C section shown below. And we have a couple of different axes that are given here. Let me go ahead and draw these in. This is going to be the x-axis here, and this is going to be the y-axis there. So I think we worked this problem out when we were going through statics. One of the example problems, we learned that the moment of the centroid of this section is at x bar equals 1.557. So that's a given value. We should be able to calculate that. You guys should be able to calculate it as well. So the goal of this is to find the moment of inertia I sub x and I sub y. Now, I should have been a little bit more careful. I should have drawn this in here as I sub big Y and this as I sub big X, like that, to separate these from the local axes. So let's do the easy part first. Let's find I sub X first. So we'll do that. And what I'm going to do is I'm going to look at this a couple of different ways. The first thing I'm going to do is break it down into 3 areas like this. So I'm going to have area number 1 there, area number 2 there, and area number 3 there. And then I'm going to take the moment of inertia of each of those. And so in doing this, I'm going to have an x-axis here. I'll call it little x sub 1. I'm going to have an x-axis here. I'll call it little x sub 2. And there's an x-axis here. I'll call it little x sub 3. So I have these centroids of these local areas. If I had a sharper pen, I could make that look better, but I don't. And so I can calculate the little moment of inertia I sub little x1 is equal to the base times the height cubed over 12. So the base of that section is equal to 4 inches. I'll drop the units just so my writing is a little bit clearer. And the height is 1 inch, and we divide that by 12. So what we would end up with is 4 divided by 12 gives me 1/3. And here I will include the units, inches to the 4th. And then we can calculate let me leave a gap here. I'll calculate I sub little x2. That's equal to the base times the height cubed. And the base here would be, let's see, it would be 6 inches here minus the thickness of the top part minus the thickness of the bottom part. So the base there is going to be 4 inches. So this dimension here is 4 inches. So I can go back over here and say the base is 3/4 times the height, 4 inches cubed divided by 12. And if I punch that number, 4 to the 3rd power times 3/4 divided by 12, that gives me 4 inches to the 4th. And then the last thing I'll do is calculate I sub little x3. So this is a moment of inertia of that bottom flange about its own axis. And the base there is going to be 4 inches again. The height is going to be 1 inch. And then we divide by 12, and we get 0.3333 inches to the 4th again. Now, you might be tempted to add these 3 numbers together to get the moment of inertia I sub x about the big x-axis, but you can't add them together because you can only add moments of inertia together when the axes are coincident, when the axes lie on top of each other. These 3 axes are parallel to each other, but they're not coincident, so we can't add them together. So what I need to do is I need to come back in. Let me use a different color here. We need to come back in and calculate the moment of inertia of the sub-area 1 about the big x-axis. So I'm going to calculate that using the parallel axis theorem, where we have this is equal to I sub little x1 plus a times d squared. I'm running a little short of room here, so let me try and write that out. So this is 0.3333 inches 4th plus the area. So 4 times 1 times the distance d squared. I usually put a little times symbol there. And the distance here is going to be this value there. So that's going to be d1. So this would be 3 inches. No, that would be 2 inches there plus another half an inch there. So that's going to be 2.5 inches, and then we square that. So let's see. I go 2.5 squared times 4, and then I add into it a third. So I get 25.33 inches fourth. Okay, now when I do the second area, I sub x2, here this is going to be equal to I sub little x2, 4 inches to the fourth, plus a times d squared. A is going to be 4 inches times 3/4. And in this case, the distance is going to be 0. So it works out that since the two axes are coincident, I really don't need to modify this, but just for sake of completeness, I'll write that out like that. And then for the third, I can come in and I can say I sub big X 3 is equal to 0.3333. That's I sub little x3 inches fourth plus the area, 4 times 1. And then this distance here is going to be this value. So that's the distance d3. And that's equal to 2.5 inches again. And that should be equal to 25.33 inches fourth. So now if I add these three numbers together, and I'll go to yet another color. So I'm going to add that, that, and this. Then I end up with I sub big X equal to 54.67 inches fourth. All right. Now, questions? Good. All right. Let me look at that problem a different way. Maybe I should have worked on this page to begin with, but I did not. So let me take this channel and let me view it as a rectangle like this. I didn't get it to right. So let's see. Go up here like that, and then over 4, down. Okay, so that's a rectangle. And then what we can do is we can subtract out from that. Let me take this. This would be the outer. We're going to subtract out this inner block like that. Now, if I take a look at this, this is the centroid of this shape over here. This is the centroid of this shape over here. So if we call that the little x, let's call it the 4 axis, and this is the little x5 axis. If I take the moments of inertia of those two sections, then I can subtract those directly to each other because those two axes are parallel and they're coincident. So I don't necessarily have to use the parallel axis theorem for that. So this dimension here is 4. This dimension is 6. This dimension here is 3.25. And this dimension here is 4 inches. So what I can do then, I can take I sub x4 is equal to base times height cubed over 12. So base is 4, height is 6, cube that divided by 12. And so let's see, 6 cubed, 4 times 12 divided by 72 inches fourth. And then I can take I sub x 5, and the base there is 3.25 inches times the height of 4. That gets cubed divided by 12. So let's see, 4 cubed, 12 divided by 3.25 times is 17.33. So then since these two axes are coincident, right? There's one axis, they lie in the same line, then I don't need to use the parallel axis theorem. I can just say that I sub big X is equal to I x4 minus I x5. And so if we push that number through, we get 72.00 inches fourth minus 17.33 inches fourth. And it works out to be, thank goodness, the same answer. All right. Now, this is a shortcut, and it works in a lot of problems because usually when we have a channel section like this, the top flange and the bottom flange are the same thickness, et cetera, et cetera. You can't use it all the time, though. You have to be careful because every once in a while we'll throw you a loop where we give you a channel section where the top flange is 1.5 inches thick and the bottom flange is only a 1/2 inch thick or something like that. And in those cases, you wouldn't be able to do this because then those axes wouldn't be parallel to each other necessarily. So, all right, let me do something for a second. I'm going to make this go away. Yeah, let's keep those, at least for now. And there we go. I need another page to work on. So there we go. All right, now we have another moment of inertia here that I want to calculate. And that's the moment of inertia of the y-axis. So let me go in and do this. This is the y-axis here. So I'm going to break this thing up into a number of sub-areas again. I'll do this. I'll take that like that. This is going to be sub-area 1, sub-area 2, sub-area 3. So here's a section there, or I'm sorry, centroid there, and centroid there. This is now going to be the y1 axis. This is now going to be the y3 axis. And this is going to be the y2 axis. Okay, now I'm going to take the moment of inertia, I sub y, and I'll do this the same way. I'll take I sub y1. So that's the moment of inertia of area 1 about its own centroidal axis. And this is equal to, you can look at it two ways. You can say this is equal to the base cubed times the height divided by 12, or you could spin the drawing by 90 degrees and then use the same formula again. So in this case, I won't write bh cubed over 12, but I'm going to use the same formula, except in this case, the base is now 1 inch. The height is now 4 inches cubed divided by 12. So let's see, 4 cubed, 12 divided by, that gives me 5.333 inches fourth. Then I can calculate here. That should give me enough room. I sub y2. This is equal to the base. The base now is equal to 4 inches. The height is now 3/4 cubed divided by 12. So let's see, 0.75 cubed. 12 divided by 4 times gives me a small number, 0.1406 inches fourth. And then finally, for the third area, I sub y3, this is equal to the base, which I'll call 1, height is 4 cubed, divided by 12 equal to 5.333 inches fourth. I can't add these three together because the axes don't line up with the big Y axis. So I need to go back now and calculate I sub big Y1. Now that's the moment of inertia of sub-area 1 about the big Y axis. And that's going to be equal to I sub little y1 plus AD squared. So this is 5.333 inches fourth plus the area A. So that's 4 into 1 times the distance d1 squared. So that distance is going to be this value here, d1. So I said that the moment of inertia, or the centroid here, was 1.557. So I'm going to take this, half the distance is going to be 4 over 2, then minus 1.557, and then we square that. So let's see, 1.557 negative 2, whoops, 2 plus, square that, times 4. Let's roll that down, 5.33 plus. That gives me 6.118 inches fourth. And then I'll jump down here and I'll do the same thing because it's symmetric. So 6.118 inches fourth. All right, now for I sub y2, so that's a moment of inertia of the big area about the major y-axis. This is going to be I sub little y2 plus AD squared, so 0.1406 inches fourth plus the area A, that's 4 inches high times 3/4 thick, times the distance d squared. So this is going to be half of 3/4. I'll just write it in as 3/8, and then minus 1.557, and then we square that. Now, one of the beauties of the parallel axis theorem is that you don't have to worry about the signs in this last term because you square it, and so the signs go away. So that helps me avoid a lot of mistakes. 0.557 minus, I square that, then times 4 times 3/4, and then 0.1406, add to that. So 4.332 is what I get. So 4.332 inches fourth. And then now if we add these three together, then what we get is I, the big Y, is equal to, let's see, 16.57. All right. All right. So let's see. Questions so far? All right, that's good. Either you understand everything or nothing. Either way, I'm happy. All right, so parallel axis theorem. And if we wanted to, we could rework this problem yet a different way. We could go in and use the positive and the negative area on this one as well. But if we did it for the y-axis, we would have to use the parallel axis theorem with the negative area and with the positive area because those axes don't line up. So I won't do that, but we could if we wanted to.